Okay, we want to look at now applying the substitution method to definite integrals. And when we do that, it's typically called the change of variables. And what we do here again is basically we're doing the substitution in here. I look at that inner function. I call that u. If our original variable is x, it's u as a function of x. That's the inner function. So we're looking for that to be inside, and then hopefully we've got u prime or some multiple of its derivative out here. Okay, so that's what we're going to evaluate. But then when we do that substitution, we need to not only change everything over to this new variable u from x to u, these limits of integration, those are going to change as well. And so the way we're going to proceed is actually to transform the entire definite integral into another definite integral, and then we're going to evaluate that definite integral. So we're going to use the fundamental theorem of calculus part 1 to do that, but we're not going to get the antiderivative in terms of the original variable x. We're going to skip that step. We're going to just go right into the new variable. Okay, and that's the amazing thing about this method. So let me illustrate how this works. So here we have now a definite integral from 4 to 11. So how would I do the substitution here? Very simply, I would let u be the inner function x plus 5. Now in this case, the derivative of x plus 5 is just 1. So du dx is 1, so du is equal to dx. All right? So the derivative of x plus 5 is 1. And so there's no manipulation at all. That just changes right over. But here's the key. We have to change limits. If we're going to change the variable, we have to change the limits. And that's something students forget to do. These are x variable limits. X varies from 4 to 11. I need to know how u varies, but we can see that if x is 4, the lower limit, then what do we know about u? U, by the formula, is x plus 5, or 4 plus 5, which is 9. And if x is 11, then u is x, which is 11 plus 5 is 16. These are the new limits in the u variable. So now in the u variable, the limits go from a lower limit of 9 to an upper limit of 16. The u is now what? Just square root of u, or u to the 1/2, and the dx is just the du. So this is what you do. You change variables. You change to a different definite integral. The value of this definite integral is the same as the value of this one. That's what's cool. You do not want to have the x limits here. You don't want to have 4 and 11 here, because that would be incorrect. If you do that on the test or quiz, you'll lose points for that. You can't use the x limits here. You have to use the u limits. Okay, again, you cannot put the x limits here. They must be u limits. I'm not unlike the substitution method where we were getting the original antiderivative in terms of the variable x, right? If I just had an improper integral, I want to know what the antiderivative of x plus 5 is. My answer better be in terms of x. Here, we don't go back to the original variable x. We are here and we evaluate this integral and we're done, using the fundamental theorem of calculus part 1. So I just proceed to find the antiderivative of u to the 1/2. We've seen that before, I think, several times. That's 2/3 u to the 3/2, right, by the power rule. Add 1 to 1/2. I get 3/2 divided by 3/2, same as multiplying by 2/3. There's no plus c because it's a definite integral. Remember, we're evaluating, what are we evaluating? U. What are the u limits again? It are these limits, right? So we can't have the 4 and 11 here. Can't have the 4 and 11. And here's the thing, we don't want to go back there because we've done this transformation. This is 2/3. Let's pull that 2/3 out. U to the 3/2, that's 16 to the 3/2 power minus 9 to the 3/2 power. Okay. So we don't have to go back to the original variable. This is done. So what does to the 3/2 powers mean? 3/2 power. The 1/2 means what? Square root and then cube it. What's the square root of 16? Square root of 16 is 4. Cube 4, that's 64. What's the square root of 9? 3. Cube 3, 27. So 16 to the 3/2 power is 64. 9 to the 3/2 power is 27. 64 minus 27 is 37. And so I get 74 thirds, and that's the answer. Notice again, I didn't go back to the original variable, and that's the way we want to proceed. So you've got to change the limits. Let's try another one here. What am I going to choose for my u this time? I hope you're saying sine of x. It's inside the e to the u function. Right? The derivative of sine of x is indeed cosine of x. So du is cosine of x dx, and there's our du. But again, we have to change the limits. You have to do this. Again, students, don't do this. You have to do this. X is 0, then what is u? U is sine of x, so this is sine of 0. Well, sine of 0 is 0. So in this case, x is 0, u is 0. Okay, you say, well, why do we have to change it? Well, look what happens when x is the upper limit of pi over 2, then u is sine of pi over 2, and sine of pi over 2 is 1. So we want to change over everything to the u world, so we have to change to the u limits. So this integral now becomes the integral 0 is still 0 in the u world, but pi over 2 is now 1 in the u world, so to speak. And this is what? E to the u cosine x dx is just du. And look at this integral is easy. You don't want to go back to the x world. So much easier here. But you got to bring these limits. You got to change these limits. You can't leave them as 0 to pi over 2. You're going to get the wrong result. It would be incorrect to write 0 to pi over 2. That would not be the equivalent definite integral. This integral here, definite integral, the value of this definite integral is the same as this one. Here it's easy though. The antiderivative of e to the u is just e to the u. I'm going to evaluate it at 1 and at 0. I get e to the first power minus e to the 0 power. Well, that's e minus 1, right? E to the 0 power being 1, and there's our answer. Easy as pie. Well, almost easy as pie, I guess half pi, right? Half pi is better than no pi. Okay, let's do a couple more so we can see how these might look. And so, what would we choose u to be in this case? We've seen this one before, right? 3x minus 2 is what I want u to be. My derivative is 3, and so du is 3 dx. I look over here, I just have 1 dx, so of course I'm going to balance mine out by doing 1/3 times both sides. 1/3 times 3 is 1. So 1/3 du is equal to dx. Okay, but then don't forget, right, I have to change the limits to the u world. And they're changed by this relationship. So if the lower limit x is 1, then u is 3 times 1 minus 2, which is also 1. Okay, well that doesn't change. When x is 2, however, I get 3x minus 2, right? 6 minus 2 is 4. So our upper limit is 4. And so this integral becomes what? So first of all, I've got 1 over u, right? 1 over u. dx is 1/3 du, so let's pull that 1/3 out. Integral 1 over u du, or just du over u. And what are my limits? We changed, right? The 1 limit, well, is still 1, but the 2, the upper limit, is now in the u world 4. So this is 1/3. What's the antiderivative of 1 over u du? That's the natural log absolute value of u, and we're evaluating that at the upper limit of 4 and the lower limit of 1. So this is 1/3. Let's pull that 1/3 out. Times what? The natural log of 4. Absolute value of 4 is 4. Natural log of 1 is 1. But the natural log of 1 we know is 0, and so our answer is 1/3 the natural log of 4. Okay. So again, we are not going back to the original variable x in these problems, unlike the indefinite integrals when we're finding the antiderivative. Okay, one more example. What's the value of this definite integral? So what's my u going to be here? My u here is just r minus 4. Notice my original variable is r. And of course, what's the derivative of r minus 4 with respect to r? It's just 1. So du is equal to dr. Okay. But again, limits have to be changed. Okay. If r is 5, then u is what? R minus 4. 5 minus 4 is 1. If r is 12, u is r, which is 12 minus 4, is 8. So our new integral is the integral from 1 to 8 in the u world, right? And I've got r minus 4, which is u to the negative 2/3 power, and the dr is the same as the du. And again, I'm not going to look back to the r's, right? I'm gone. I'm in the u world. I'm just going to do the integral here. The antiderivative, I add 1 to negative 2/3, I get 1/3. Dividing by 1/3 is multiplying by 3. So the antiderivative is 3u to the 1/3. And again, I'm evaluating at these u limits, right? Don't put the 5 and 12 here. They don't belong. It's 1 to 8. So I evaluated 8, evaluated 1, and I'm done. So this is 3. Pull the 3 out. 8 to the 1/3 power minus 1 to the 1/3. 1/3 power means cube root. Cube root of 8 is 2. Cube root of 1 is 1. 2 minus 1 is 1. I'm just going to get 3. And there's the value of the definite integral. Okay, so we've looked at the substitution method, and then we looked at it here at the end here as it pertains to definite integrals, and we call it change of variables in that case usually, but same thing. So you'll need to practice, because the method of substitution for finding antiderivatives and the method of change of variables, we're evaluating definite integrals, is going to be used all the time from now on out. So we need to be ready and prepared to do that. Okay, we'll end the video now.